Hello, hello.
What's going on, Alex and Camille? Hello, happy Thursday, everybody. Can you believe it's Thursday?
Yes.
I mean, I guess intellectually I believe it's Thursday, but deep down inside, I really think it's Wednesday. Again, weeks go by a lot quicker for me these days. I don't know about you guys. I don't know why that is. But anyway, how's it going? How's everyone's Thursday happening? / Wednesday. It's swell. Thank you, Lauren. the, the Thursday crew, always the positive attitude. What's going on, Herman? How's it going? We're just talking about how our Thursdays are going swell. I mean, Thursdays are Friday's Friday, which are great. Like, okay, wait, what's everyone's favorite day of the week? Let's start with that. Here's what I'll do. I'm gonna ask. Go to the days of the week. Press the little raise your hand button when you get to your favorite day. Monday. No surprises there. Tuesday. Wednesday. Thursday. One for Thursday. Really? Why is that? Are Fridays like super easy and so it's basically the start of the weekend?
I don't know. I've just always kind of liked Thursday. For whatever reason, like timing wise, a lot of things are nice on Thursday. Like a lot of stuff ends up getting pushed onto Friday so Friday's kind of awful sometimes.
Oh, that's what I was expecting.
Well, right, because like some people just put stuff off until the very end of the week to happen.
Yeah.
But
Which is why
nice.
I've experimented before with classes of having homework due Thursday instead of Friday. Purposely to make it so it's like, hey, now your Friday's nice. But people don't like that sometimes. Camille, so are you Friday or Saturday or Sunday?
Oh no, I like Thursday.
Oh, we're all Thursday fans.
Yeah.
That's the most interesting thing I've ever heard. No wonder you guys are all here today because you're like, Thursdays, have some fun, let's do some discrete math. Anyway, I think I'm firmly a Friday guy myself, but now I feel we're pretty basic with that now that everyone loves Thursdays. I mean, I get the appeal. I just feel like we keep pushing back our excitement for the weekend. It's like, oh, like people used to love Saturdays. So it's like, hey, we actually have a day off. And they're like, you know what? No, Friday's kind of nice because it's like the excitement of the day off is even better than the day off itself. But then it's like, you're so excited about Friday, Thursday becomes the great thing. That's my theory. It kind of goes against Alex's point. But anyway, the point is, today's Thursday, so let's have some fun under your favorite day of the week and get started with some more discrete math. And today we're going to do some more of this divisibility stuff we've been talking about, which is fun. And divisibility is kind of cool because it's easy enough definition that like right away we can start we can get into it and actually prove some interesting things. And today we're going to end with what's called the fundamental theorem of arithmetic. Yes, that's how important it is. There's the fundamental theorem of algebra. There's three fundamental theorems that you guys have probably gone over in your life: the fundamental theorem of arithmetic, algebra, and calculus. And I think we're only going to do the arithmetic one in this class. But anyway, so it's going to be fundamental. It's going to be awesome. So let's just start off with a really nice divisibility fact that's super easy to prove. And we're just going to prove it real quick so we can use it. So we are in our divisibility proof. So we're kind of somewhere in the 4.3, 4.4 range. It all blends. And yeah. So here's the claim. I mean, now we're in the part of the class where it's kind of awesome. It's just going to go like claim, proof, claim, proof, claim, proof, which is kind of the fun part. Let's just get to thinking here. So the claim is that A divides B, or I'll say whenever A divides B, A will divide B times C for any integers A, B, and C. This isn't a really casual way of saying it. I might as well have added a bruh at the end, right? This is just like the English, like but the point is, what's this saying formally? Like, let's just kind of get rid of any interpretation differences. What's this actually saying? First of all, is it a universal statement or an existential statement?
Universal, right? For all
Universal,
A,
right?
B, C, and the integers.
Exactly. And so what I'll say is be careful here. It's kind of tempting to say like for all A, B, and C and Z.
Z cross Z cross Z.
Yeah, which totally makes sense. However, what we really need to do is we either need to talk about A, B, and C separately or talk about A, B, and C as a group. So what I mean by that is the actual formal way to write this would be for all A and Z, for all B and Z, and for all C and Z, we get that whenever A divides B, A divides BC, otherwise known as if A divides B, then A will divide BC. So what I'm saying is A divides B implies A divides BC. All right. Or what you could do if you really want to, if you really wanted to get fancy, is you could consider A, B, and C a group, and you could say for all ordered triplets, A, B, and C in the set Z cross Z cross Z, AB implies A divides BC. It depends what you want to do. I think the top one's more common. It's not wrong, maybe easier, but the bottom one's also not wrong. So do as you wish. Well, the point is, yeah. So this is the formal claim, and the first
Quick question.
Yeah.
Is there a difference between Z cross Z cross Z and Z3?
Nope, they're the same thing. Actually, this it's this equals Z3 is out of saying because it actually follows the exact same notation as like algebra, where like 2 times 2 times 2 equals 2 cubed. Same exact idea. And there's reasons why we call this multiplication. There's also a form of kind of set addition, but that's all abstract algebra nonsense. Actually, it's sense. It makes sense. So that's just a bunch of abstract algebra sense. Well, that's for like 5 classes from now, 6 classes, whatever it is. So we'll leave that for them. You know, we can give them something. You know what I mean? We can't have all the fun in this class. So the point is, yeah. So this is the claim, and here's the question: is it true? Let's do our little aside here, and see. Like, what do you guys think? Do you think this will always be true? Can we ever break it? Well, first thing maybe is do an example to see does this make any sense at all. So let's see, like for example, 3 divides 6. And if we pick any integer c, like 2, 3 will divide 6 times 2, which equals 12, right? 3 does divide 6 because 6 equals 3 times 2. And 3 does divide 12 because 12 equals 3 times 4, right? So we have 3 times an integer multiple is the point. So it worked for 3.
A probably can't be 0, right? Like you can't have 0 divide something.
Well, I kind of see what you're saying, but actually the statement kind of works itself out, right? So if 0 divides like 0 divides, so remember, we'll say A divides B. By definition, that means that there exists a K and Z such that B equals AK. So if we're saying 0 divides B, what's that saying? That there exists a K and Z such that B equals 0 times K. But 0 times K for any integer K, we know it's going to be 0. So the point is, you're right. 0 divides B only if B equals 0. You're totally right. However, right, we're just saying that if A divides B, then A will divide B times C. So if A was 0. So in the case where A is 0, if 0 divides B, well, that means B is 0. And so then 0 will divide B times C no matter what C is, because that's going to be 0 again. You see what I'm saying?
Sort of, and otherwise it would be like vacuously true, right? If B is right, if 0 doesn't
Exactly.
divide B.
Exactly. All we have to prove is that in the case where A divides B, it will divide B times C. And so let's actually kind of get a little down and dirty with the math here. So A divides B, what's that mean? That means there exists a K such that B equals AK, right? But now, let's look at B times C. B times C, based on this, well, B is going to be AK. It's going to be AK times C, otherwise known as AKC, right? So from this, we can see we didn't really have to consider if like 0 in all these cases, because the point is, this actually kind of this kind of actually brings up the beauty of direct proofs again. The whole idea of a direct proof is like you're not looking at specific examples, but instead you're just looking at just general properties, right? And the A divides B, the property that A divides B, what that means is that leads to the property that there exists a K such that B equals AK. And having that property means you multiply it by C. Well, we can do this whole thing with the associativeness of all that, and you get A times KC. So having A divides B will lead to that, and will lead to this in general. It doesn't matter what A, B, and C are, just the property of A dividing B will lead to this being true, will lead to the property of this being true. And so we don't even have to consider we don't have to consider anything. We just see, oh, it's gotta be true. Does that make sense? Hope the answer there is yes. The point is that we just follow the math, follow the algebra basically here. We can see like every step along the way we did a valid operation, and so we can't possibly be false. So yeah, but the 0 thing, if we want to get into it a little more, just to make us just to kind of give her that little nagging feeling of like, what about that? If 0 divides B, that means there exists a K such that B equals 0 times K. 0 times K always equals 0. So 0 divides B means that B must equal 0. Then for any C, B times C is going to equal 0 times C, which is 0. And 0 does divide 0 since, for example, 0 equals 1 times 0. It's an integer multiple. This is weird. This is weird because this is where divides and division divide. This is where they separate, right? Because we're not saying that 0 divided by 0 exists. It doesn't. This is undefined. And the reason it's undefined is because you can actually put a 2 here and a 3 here and a 4 here. You can put anything. You can put any integer multiple here to work. But the point is 0 divided by 0 is undefined. So the division of 0 with 0 is undefined. But by our definition of divides, 0 does divide 0, since you can find an integer multiple to multiply 0 by to get 0. It's kind of complicated. It's not really complicated, it's just like messy because you have 0 running around everywhere and stuff like that. But I hope this sinks in and makes some sense. Any questions? What if I smile louder? Okay.
So what's the logical difference? So I get that we can prove it using logic that 0 divides 0, but 0 divided by 0 is undefined. Like, what's the logical difference between those two things?
So
you know what I mean?
Yeah.
Like, so, I understand it, but I don't innately understand what the difference is.
I think the key is that divides and division are clearly related, but they're just different. So by definition, A divides B. What that means is that there exists a K such that B equals AK, where A is an integer multiple of, where B is an integer multiple of K, is what I want to say. Like you can multiply by an integer and you can get B. But it's a there exists, right? Here's kind of the key. It's going to get a little complex. So people, what I'm about to say in the next 5 minutes, you don't exactly need to know fully, but it's a good question. So this just there exists. It just says there exists a K, right? But here's the definition of division. A divides C equals B. What that means, and we're going to learn a symbol here, is that or what that means is that I'll put a K here. No, I'll put a K here. Yeah, this is what I'll do. A divided by B equals K. What that means is that, no, sorry, this is what I want. This is the setup. Here we go. B divided by A equals K, because it's kind of like the same order we have it here. B divided by A equals K. What that means is that B equals AK, and K is the unique number such that B equals AK. That's really what it is. B divided by A defined means there exists a K such that B equals AK. This exclamation part here, this means unique. This means there exists a unique K. And so B divided by A defined, what that means is that there exists a unique K such that B equals AK. That's kind of like the definition, because otherwise, kind of like how would you define it? Because we kind of define, division is like literally defined as being just kind of like the reverse of multiplication. And so when we're doing B divided by A, the question we're asking ourselves is, okay, what can we multiply by A to get B? Right, that should be the answer. But what if there's two things you can multiply by A to get B? Right, well that's like, which one do you pick? That's why we call it undefined, because literally we just don't have a good reason to pick one over the other. And you might say, well, when would that come up? Well, 0 is the exact case when it comes up. So for example, notice that 0 equals 0 times 1. 0.
You're off camera a bit, Professor.
What? Oh,
you're
sorry.
Off camera a bit.
Yeah, 0 equals 0 times 1, 0 equals 0 times 2, 0 equals 0 times 3, 0 equals 0 times anything, right? You can keep going like this. So the point is, 0 over 0, right? There is not a unique K such that 0 equals 0K, which is why 0 over 0 is undefined. But so the definition of division basically involves a unique K, because we actually kind of want to get an answer. The definition of divides just means there exists a K. And so here there exists a K. There's just plenty of Ks. That's the reason 0 divides 0, but the reason that 0 divided by 0 is undefined, because there's more than one. Like, which one would you pick? Would you pick 1, 2, 3? What would you pick? Yeah. Good question, Herman. I hope this at least gives you an idea of the difference.
That makes 100% sense.
So to make a just quick analogy, is like division like more of a functional thing, whereas divides by is more of the relation?
Exactly.
Okay.
Division gives you a number answer. whereas divides gives you a truth value. It's either true or false. And so the number answers are more complicated. It's just like, what if there's more than one? And then the reason that like that when you divide by 0, the reason that's undefined isn't because it's just because you can't find anything. That's because there does not exist a k. There is no k such that 3 equals 0 times k. There exists none. You can't reverse that division. It's like, what do I multiply 0 by to get 3? Well, there's nothing that exists. So it's kind of the opposite of 0 divided by 0. 0 divided by 0, everything would work. 3 divided by 0, or anything that's not 0 on top divided by 0, nothing will work. So that's why it's undefined. Because you need there to exist a unique k. So existence and uniqueness are two properties there. Anyways, as interesting, and by the way, the 0 divided by 0 thing leads, this is calculus. The idea that, well, what do I say? Like, what's the k, where 0 equals 0 times k? That's basically the derivative. It's a whole thing. It's interesting. But anyway, so we can talk about that later. But for now, I think this makes sense. Let's just do this proof. Let's do this proof and move on. I think this proof is probably the easiest division proof we've done so far. So the proof, we went with the logic already. So we start every proof, right? Well, it's a for all proof. So we start it with the particular and arbitrary thing, right? So let A, B, and C be particular, actually, let's do arbitrary first. It sounds better. Be arbitrary, but particular integers. Now, the whole thing about proving an if-then statement, that to prove an if-then, I'll say, remember, to prove an if-then, just need to show that whenever the hypothesis is true, the conclusion will follow. So all I'm saying here is we don't care about when A divides B is false, because when A divides B is false, so this whole thing's vacuously true, so we're good anyway. We only need to concern ourselves with when A divides B is true. And so we're just going to say assume A divides B. And so we need to assume A divides B, and then from just this information, because these are arbitrary but particular integers, they're just integers. We know nothing about them. We don't know if they're even, if they're odd, if they're prime, if they're squares, whatever. All we know is A divides B. We need to use that information to show that A must divide B times C. All right. Well then, what's the first thing we do usually in all these division proofs, all these divides proofs? Like eventually, right, we're going to want to say, eventually we're going to want to prove that BC divides A. Or, sorry, A divides BC. And so eventually we're going to want to say, like, consider BC. Note that BC equals, they want to put a bunch of stuff here to eventually get an A times something, and that'll prove what we want, right? But to get to that, what do we need to do?
Do we kind of start with the definition of divides and like
Start with the definition. I think that's a great idea, right? Sometimes when we've been doing like higher level proofs, you'll keep divides like this, and you'll use some theorems that you proved about divides to help us there. But for these kind of low level things, it's kind of the only thing we can do at this point is just expand out what this means. So then, by definition of divides, there exists a k in Z such that B, or I'll say, yeah, AK equals B. What do you want to say? All right. Now that gives us something to grab onto, right? Now we just like divide. It's like, well, this is the truth value. This gives us some numbers to play with, right? We know there's an integer k. Let's play with it. So then note BC. Well, now kind of like the only thing we have to do is substitute what we know for B. So we know B is AK. So BC equals AK times C by substitution. And now we're almost done. This just equals A times KC by associativity. And associativity, remember, says we can move parentheses, which we know is true with the real numbers and multiplication. So we're good there. And by the way, it has to be the same operation we're doing, right? So it is true that like, it is true that A times B times C is the same thing as A times BC. It's also true that A plus B plus C is the same thing as A plus B plus C. Totally fine. What's not true is you can't say that A plus B times C is the same thing as A plus B times C. This is not true. You might say, well, we just move the parentheses around, and associativity works with multiplication and addition, right? But it has to be like a homogeneous thing, like all multiplications or all additions, you can move it around. Clearly here you can't do it because you need to use the distributive law, which is nice. Which I think we've done enough algebra in our lives where this is obvious, but for other things, like, you know, I've seen this mistake with like P's and Q's and ands and ors and stuff. But the point is, yes, that's what associativity means. But anyway, we're basically done, people. Case is an integer. Why is K times C an integer?
Closure under multiplication.
Closure and multiplication, right? K and C are both integers by definition. Integers are closure and multiplication. K is an integer. So we've written BC literally equals A times an integer, which is the exact thing, the exact definition for being, for A dividing BC. So what this means is, so the note K and C and Z by their respective definitions, K here, C here, and the integers are closed under addition. So K times C is in Z. Therefore, since K times C is in Z, BC, which equals A times KC, is divisible by A by definition of divides. Done. So saying BC is divisible by A is the same thing as saying that A divides BC, just kind of written out. Any questions? Good. I think this is pretty obvious. This is just saying that if A divides B times C, clearly, because just adding an extra thing on top of it, that's fine. Yeah. I won't spend any more time on that. Cool. Can I erase? Then I will. All right. feel. Oh, I threw baseball yesterday for the first time in a while. My arm is killing me. I am too young for this. Okay. Here we go. Yep. Okay. So next up, so that's a nice little division proof right there. And by the way, now that I proved it, you can use that anywhere in your homework or tests or anything. It's very useful. Next up, let's prove this little ditty, which is, or prove or disprove, I should say. And the claim is I'll come back, I promise. For any integers a and b, let's look at how well. For integers a and b, if a divides b, come on. Oh, okay. No. Is there something else? Why? Sorry for the technical difficulties, everybody. Usually when I scribble, it just kind of comes back, right? Let's just pretend. I'll draw a smiley face. That's a haunting face. Oh. All right. Well, anyway, I'll just tell you what I said and we can talk about it while we wait for this thing to come back. And that is, I said if A divides B and B divides A, then A equals B. What do we think about that? There we go. Well, let's think about it. I mean, 3 divides 3, and 3 divides 3, and 3 equals 3. So there's some evidence there. But really, what we're kind of showing here is more the reverse direction. That, and maybe I should put that instead. Instead, I should put A divides B, then B decides C if and only if A equals B. So clearly, if A equals B, this works. For A divided by B and B divided by C, well, I mean, think about A dividing B. The relationship for A and B, you know, we kind of draw it out like we've been talking about a little bit here, right? Like, I don't know. Like this kind of diagram right here, I'm kind of saying that 4, 1, 2, 3, 4, divides 8. 1, 2, 3, 4, 5, 6, 7, 8. Because 4 can kind of evenly fit into 8. You can divide 8 evenly into groups of 4, right? That's kind of what this is saying. But notice if you're dividing a number into groups of other numbers, those other numbers, in a certain sense, have to be smaller, right? Those groups that you're dividing into have to be smaller or the same size, right? Because 8 does divide 8. But the point is it can't be bigger, right? Like you can't divide 8 into groups of 9, right? This is kind of making sense, right? You can't divide 8 into groups of 9. You can't divide 8 into groups of anything bigger. So if A divides B, I'll say then maybe, we haven't proved it yet, but then maybe A is less than B? If that were true, if true, then A divides B would imply A is less than B. B divides A would imply B is less than A, or less than or equal, I should say, right? Because like we said, 3 does divide 3. So if A divides B, then A is less than or equal to B. If B divides A, then B is less than or equal to A. Well, then together, if A is less than or equal to B and B is less than or equal to A, it's going to equal B, right?
Is that exclamation mark just a normal exclamation mark?
What?
Is that exclamation mark just a normal one?
Oh, yeah.
Okay.
Yeah. That's probably math. You can't get excited because the exclamation mark's used for like 3 different things. But yeah, so this is seeming to make some sense, right? And by the way, I mean, this just makes sense that A is less than equal to B and B is less than equal to A. The only possibility is that A equals B. But you can actually prove it because A is less than or equal to B. What that's saying, that's equivalent to A is less than B or A equals B. And B greater than or equal to A is equivalent to, B less than or equal to A is equivalent to B less than A or A equals B. And these two are kind of opposites of each other, so we can kind of use an elimination argument to prove that A equals B has to be true. But anyway, do we see any problems with this? Can you, because I said maybe, right? Can anyone think of a situation where A divides B, but A is not less than or equal to B?
The negative of number.
Negatives. Negatives totally screw us up, right? I mean, for example, 3 divides -6, but 3 is not less than or equal to -6. The exact opposite, -6 is less than 3. So that totally screws up this idea. But then wait a minute, this might lead us to a different thing, and that is what if we just use -3? 3 divides -3, right? Since -3 equals -1 times 3, we can find it's an integer multiple of 3. But also -3 divides 3, since 3 equals -1 times -3. So this is our counterexample, right? This just shows right here that there is an A and B, 3, -3, for example, or you could use any two opposite integers like this. And A will divide B. Oh, this should have been B divides A. My bad, people. There's no C here at all. The point is, here A divides B and B divides A, but A does not equal B. So this is not true. We can't say this. Does that make sense? And by the way, we should have written it formally, which says that for all A and Z, and for all B and Z, A divides B and B divides A, if and only if A equals B. And so it actually is true that if A equals B, A will divide B and B divides A. We kind of talked about that a little bit, but it doesn't work the other way around. And for an if and only if to be true, like this is equivalent to saying for all A and Z and for all B and Z, A divides B implies, that this side implies this side, and then all of this and the other way. For all A and Z, for all B and Z, A equals B implies A divides B and B divides A. So it's an and statement, right? So to disprove it, you just need to prove that one of them's false. And even though this one's true, this one's false. So that's enough. So prove. Or disprove, more like. So here, it's a universal statement, right? And so we disprove a universal statement by counterexample. So I'm going to say disproof by counterexample. And what do we want A and B to be in our counterexample? I said 3 and -3, but what do you guys want? This is not my proof, it's our proof. So what do you guys want? $42. All right, almost the answer like the universe and everything. Also Jack Robinson's numbers. That's great. But anyway, so disproof by counterexample. Let A equal 42 and B equal -42. We could have done the other way around with B equal -42, A equal 42 does not matter. What's like after we pick out out the things we use in a counterexample, what's the first thing we do in every counterexample proof?
Do we state the negation of the statement we're trying to disprove formally, or?
We don't really need to. You could if you want to help you out. And so in our case, the negation is that there exists an A and Z, and there exists a B and Z such that A divides B and B divides A, and A is unequal B. Or A does not equal B, and or A equals B, and A does not divide B, or B does not divide A. If you work it out, this is the negation of this. The reason being, well, this is the negation of this guy here, and this is the negation of this guy here. And the point is, since it's an if and only if, there's two ways it can fail. Either the first way doesn't work or the second way doesn't work. And so this is saying the first way doesn't work, or this is the second way doesn't work. If either one doesn't work, if and only if fails. But
Okay, then do we verify the domain?
Exactly. First thing you do is verify A and B are all what we care about. And what that means is that in the domain, and specifically for universal conditionals, we care that the hypothesis is true. So we care that since we're disproving this side, we show that A and B are integers, and this hypothesis happens. So note 42 and -42 in Z, and actually, just to avoid run-on sentences, further note B, which equals -42, equals -1 times 42, which equals -1 times A. So, since -1 is in Z, A divides B. Right? All we did there is we proved that A divides B. We proved that 42 divides negative 42 by showing that there's that negative 42 is in fact an integer multiple of 42. Also, A equals 42, which equals negative 1 times negative 42, which equals negative 1 times B. So since negative 1 is in Z, B divides A. So our hypothesis is true as required. You don't necessarily need to write this part, although, you know, for proofs, it's always nice to kind of walk your reader through what you're talking about, right? Because proofs are kind of meant to be read. And so it's always nice to say, like, we're doing this now because of this. So our hypothesis is true as required because we're doing the counterexample thing. So far, all we've shown is that we have picked an A and B where A divides B and B divides A. That's all we've shown so far. But, well, I'll say, however, now the counterexample part for this is really easy. However, 42 does not equal negative 42. We're allowed to know that integers aren't equal to each other, right? That's the thing we're allowed to assume. However, 42 is not equal to 42. So the conclusion is false. Therefore, there exists integer A and B, mainly 42 and negative 42, with A divide B and B divide A, but A does not equal B, hence our claim is false. Any questions? Yeah, I think it's pretty simple, right? I mean, this is like, well, once again, counterexamples are in a certain sense, they're definitely, the proof part is easier. Like getting to them might be harder because you have to think of maybe a kind of weird example, but actual proving is easy. You just say, here's A and B, doesn't work, go home. Well, everybody, we're done. But yeah, so you good? All right. So that's not true. But it's almost true, right? What could we change about this statement to make it true?
Could we absolute value A and B?
We could absolute value A and B, or what I'm going to say
We could square A and B.
Oh, that's actually an interesting idea too. What I was going to say is for any positive integers. A and B, A divides B, and B divides A, if and only if A equals B. I'm going to state an algebra fact that you're allowed to know. Here's your algebra fact. If K is greater than or equal to 1, and A is greater than 0, then K times A is greater than A. It's not even really an algebra fact. I mean, I guess we could prove this, right? It's saying that, yeah, or greater than or equal to A is what I want to say. Like K is greater than or equal to 1, and if A is equal to 0, by inequality algebra, we can multiply A by both sides, and we get that AK is greater than or equal to A. So, yeah. But the point is, be thinking about this. Be thinking about this. So if we want to prove this, right? If we want to prove this, notice that we start with A divides B, and B divides A. Well, then this leads to B equals KA for some K. And this leads to B equals, I'm sorry, A equals CB for some C, right? The point is it's an integer multiple. B is an integer multiple of A, and A is an integer multiple of B, right? And remember, we have to use different variables here because they could be different, right? We don't know they're the same thing. That's a key part. Different variables. If you don't know they're the same, use different variables. Just done. That'll always mess you up. But anyway, so then if we have this, right? Notice, hey, we could plug this into here. Or we could plug this into here. I'm gonna do it this way. So if we plug that into there, we get that A equals C times B, which equals C times KA, which equals CK times A. Right. But then, if A equals CK times A, well, I guess there's a couple ways you could do this, right? You could start here and go, if A equals CK times A, well, since A is positive, for one, it's not 0, because 0 is not positive or negative. So that means we can divide both sides by A, and then you get that 1 equals C times K. And then the only divisors of 1 are 1 and negative 1. So that means C equals 1 or negative 1, and then K is going to equal the same thing as C. Because if C equals 1, well, K's got to be 1. If C equals negative 1, K's got to be negative 1 to make it work out. But then we can notice that since A and B are positive, K and C can't be negative 1, so K and C are both 1, B equals A. We could do that, but let's make use of this algebra fact right here, because we have it. Let's kind of go the other way around. So notice if B equals KA, right? K is in Z, right? And in particular, since in particular, K equals B over A, since A does not equal 0 because A is positive. And since B and A are both positive, K is going to be positive. And same thing here. C equals A over B. So C is positive, right? And if you're a positive integer, all positive integers are greater than or equal to 1. Does that make sense? Because if we look at the integers, we have 0, 1, 2, 3, negative 1, negative 2, negative 3. All positive integers are bigger than or equal to 1. So that means K is greater than or equal to 1, and that means C is greater than or equal to 1. But then we can use our algebra fact, right? By this algebra fact, since C is greater than or equal to 1, right? A, which equals C times B, is going to be greater than or equal to B. And since K is greater than or equal to 1, B, which equals K times A, is going to be greater than or equal to 1 times A, which equals, is going to be greater than or equal to A. So B is greater than or equal to A, and then A is greater than or equal to B, thus A equals B. Does that make any sense? Okay, but sadly it's 5 o'clock, and so we're gonna finish this next time. So no, I don't want to rush through this. But yeah, so it is gonna be true that if A divides B and B divides A, and A and B are both positive, A equals B. And that should kind of make sense for the reason we're talking about with like, if A divides B, that means you can divide B into like you can evenly divide B into groups of A, would mean A must be less than or equal to B, and same other way around. This is how you prove it. Well, that's all we got, people. Good week. Happy Thursday. And I hope you have a good Friday, even though apparently just the week's all downhill from here for you people. This Thursday's great, and Friday, Saturday, and Sunday, and then we start again on Monday. Just living for Thursdays, apparently. Is there any questions? Cool. People, I'll make an announcement. I might delay quiz 4.4 just because I don't know if we actually got to what I don't know if we got through it all. I'll see what the questions are, make sure we get through it all. But anyway, there'll be an announcement about that if there is. But other than that, we're done. We're done. Next week we start, wait a minute. Yes. Next week we start proof by contradiction, which is my favorite thing in the world. It's amazing. It's really fun. So just to keep you on the hook. But yeah. 5 o'clock. Have a good day.
Take care, Professor.
Yeah, bye Alex. Bye Herman. Have a good weekend.